working with PLFA, the next slide scares everybody because we've seen this before. When we talk about soil, we talk about the biological, the chemical, the physical, where the three of those things overlap. That's what we generally define as soil health. This is what that looks like from a soil testing perspective. I know that text is hard to read, but we've got physical health, we've got texture, soil structure, porosity, pore size distribution, water retention, et cetera, et cetera, et cetera. Chemical, things that we think of, reaction, cation exchange capacity or CEC, nutrient reserves, soil biology, or the biology, soil biodiversity, organic carbon. I mean, can you imagine the amount of data you could collect to try to really evaluate soil health? It's overwhelming and it's very, very expensive. And so expensive is not really the direction we want to go, right? Right. Okay, just making sure. Because if not, I mean, I'll promote all the tests and I'd be more than happy to take one sample for $500. I mean, no, that's not the goal of this. The goal of this is to pick out the tests that we think are the most meaningful, the most impactful, offer you the most amount of information to try to help you figure out, you know, what the ramifications are of what you're doing or maybe what direction you want to go. So, if we jump into, if we can hit the right button, PLFA. PLFA is a wonderful tool because every living organism is made up of cells, and those cells are made up or covered in membranes. That cell membrane, we're going to use that to our advantage. Soil does not naturally have membranes, and it does not naturally produce fat. Short part of this story is that when we run PLFA, we're extracting fat out of your soil. We want to know how fat that soil is. And I'm happy to say the fatter the healthier. I guarantee it. So what we're doing with this is that basically we extract these fats. They're quantifiable, means we can actually measure them in the lab. They do represent living biomass, and they respond very quickly to management changes because when a cell dies, bacteria die very quickly. Some of them live for a matter of hours to a few days, and fungi maybe a few weeks before they're reproduced. So when the cell dies, we need these fatty acids to disappear quickly. Otherwise, you get what's called an artifact. If we start measuring, you need something that's going to respond to what you're doing. We need something that will respond to management. Otherwise, we're just looking at something that happened 10 years ago. So that also makes this test pretty powerful. Anybody remember high school biology? Did anybody attend high school biology? Okay, me either, I guess. I stole this out of a textbook, The Anatomy of a Cell. And then I stripped it down to show you this is what a membrane looks like, looking at it from the side. There's all kinds of stuff here. If we strip this down even further, this is what we're left with. This is called a phospholipid bilayer. That's where the term phospholipid fatty acids comes from. This is the part of the membrane that we're actually dissolving into solution that we're measuring. Now the neat thing about phospholipids and looking at PLFA is that we don't actually have to count the microbes to understand how many of them are there. Now, what we're actually doing is we're quantifying the amount of fat in the soil, and we add that up and we get the higher that number, the higher the biomass, and the higher the biomass, the better. A lot of you saw this table today and we went through it. So I'm not going to spend a lot of time on it. But the real meat of this is kind of with these PLFA report ratios. And we went through 3 out of the 4 of these today for the people that we did individual consults for. But I'll kind of go through each of them a little bit more now. So generally on PLFA, the higher the fungal number, the better. And it does relate to management. You know, we talk about reduced soil disturbance, increases in carbon inputs. And I did talk a lot about pH today. 5.9, I remember. For the low pH award winner, 5.9. And most of the soil pHs are running, 7.5 to 8, or maybe even 8.2. you have an unfair disadvantage there. Bacteria tend to dominate or have an advantage in alkaline landscapes compared to fungi. They just do. It has nothing to do with your management, it just has to do with their physiology and what they're able to withstand. But don't be deterred by that, because we can build fungi in the soil through carbon inputs, through reduced tillage, and in some cases, I saw a lot of examples today of vegetable production. I love no-till, but obviously there are situations where it's gonna happen. I'm not gonna look down on anybody for doing tillage. It's what you do around the tillage that really makes a difference. And I saw fungal population numbers today off of a lot of tillage operations that actually remind me a lot of 30+ year no-till corn bean rotations back home. Because tillage is not really the biggest problem, it's fallow. We have to feed microbes, fungi especially. Mycorrhizal fungi are obligate symbionts. Now what that means is they don't survive without a living plant root as a host. They could care less about tillage because we're starving them to death, right? So it's fallow is really the big enemy. It's those dead periods, or those periods in between where we don't have anything growing. So where we see some tillage, but we see a reduction in fallow, we see carbon inputs, we actually see fungi respond very positively. So it can be done even in those types of systems. We have this, kind of ranking table here, and for a lot of us today, when I talked about this ranking table is not specific to this region. It's not specific to any region. It's just the combination of thousands of samples that we've put the data together and tried to make some kind of rank so we know kind of where we start. Everybody wants to know what the number's supposed to mean, right? Because I can generate data all day long, but we have to be able to understand in context of what that means. So it ranges anywhere from less than 0.05 to 1 up to 0.35 to 1. A quick note on, I can tell in this room, just based on what Elizabeth said about the pamphlets, I bet every one of you goes home at night and reads like scientific literature on fungus. I can just tell. This seems like that kind of crowd. And the issue is that whenever we talk about this, you hear a lot of different things about fungal to bacterial ratios. Has anybody heard of the fungal to bacterial ratio before today? Okay, and usually when people talk about it, they want a 1-to-1 relationship. Equal parts fungus, equal parts bacteria. Using PLFA as a measurement tool, you will never get 1-to-1. The reason is because bacteria have a larger amount of phospholipids per pound, or whatever you want to say, than fungi do. So it's an unfair advantage that we add weight to fungus. That's the reason why our scale says 0.25 or 0.2 to 0.25. That's essentially 1-to-1. So if somebody looks at this and they try to argue with you when you're showing them your results and talking about your progress that you're not doing a very good job because you don't have any fungus, just tell them Lance Gunderson told you. That's not going to help you. Tell them anybody else told you. I don't care. That a 0.25 is essentially 1-to-1. And that's important to keep in mind, because I know a lot of people get discouraged because they never see that number go up. But that's what's really happening. The predator to prey ratio is a combination of looking at protozoans to bacteria. It was mentioned earlier tonight that protozoans graze on bacteria in the soil. And they do so in macropores and micropores. They swim through channels in the soil, so the soil structure becomes very important. Also, the abundance of bacteria has to be there to feed these organisms. Now, you're probably sitting there going, now why do I care if I'm feeding protozoans? And it really boils down to nutrient cycling. And a lot of times we focus on nitrogen, but it's most nutrients. And when we talk about a bacteria cell, how many of you have heard of the term carbon to nitrogen ratio? Man, that's a confusing topic. We're going to talk a lot about that one, but the reason why it's confusing is because there's 1,000 carbon-nitrogen ratios we can talk about. the cover crop mix that you're growing, the cash crop you had the year before, what the residue is at the surface, the water soluble extract on the Haney test. Well, here's another one. Bacteria have a C to N ratio of around 3 to 1. Does anybody know what the C to N ratio of alfalfa is? Around 25 to 1. Corn at maturity, 80 to 1.
Wait, I'm sorry, the what ratio?
Carbon to nitrogen.
What do you think?
C to N, yep. Sorry. Yep, carbon to nitrogen ratio. So corn is about 80 to 1, wheat's 80 to 1. The trees, 300 to 1. So in other words, bacteria have a really strong affinity and need for nitrogen. More so than any crop you can plant. So who do you think has a competitive advantage to tie up nitrogen in that soil? Is it the crop or is it the microbes? Microbes. Microbes have the ability to tie up nitrogen. Now, protozoans, on the other hand, they have a carbon to nitrogen ratio of around 15 to 1. So that means that they have to consume 5 bacteria cells to get 15 carbon, but now they have 5 nitrogen. What happens when we feed a really high protein feed to livestock? They poop out. Lots of nitrogen, right? I mean, they tie up what they need, they have what they need, and the rest of it gets excreted as waste. That process that's happening in the soil, or on the soil, above ground, is the same process that's taking place below ground. And we call that mineralization. So it's taking organic forms of nutrients. And when I say organic, I don't mean necessarily fish meal or bone meal, those types of things. I just mean in the organic form, meaning nitrogen tied to carbon. It's protein, amino acids, etc. Just like when we consume food, the microbes do the same thing, and then they release nitrate and ammonium, and that's what your plant's going to use to produce more protein and more organic in. So you see the cycle. Oftentimes in agriculture, though, we disrupt the cycle because we put on really large amounts of synthetic nutrients, and then we grow something, and then we haul it off, and we ship it somewhere far away, and then we start over again. It's worked to some degree. I use the term worked. I mean, we've produced a lot of food, but it's a really inefficient system, and it's really getting to be more and more expensive. And there's environmental impacts, and we could go down 100 different paths, right? But that's kind of the idea, is that we want this process happening in the soil. We want the protozoans feeding on bacteria to release nitrogen. In order to do that, we have to have good soil moisture, we have to minimize disturbance, and we have to have overall high biomass. The common theme to this talk is that basically most of these things can be accomplished through carbon. When we add carbon into the system, that's food for microbes. The microbes then build soil aggregates, which increases porosity, it increases water holding capacity, it allows water to infiltrate. So it really does start with the foundation of carbon. But this is a really important ratio. I talked about the gram-positive to gram-negative ratio, and I don't really want to get into this one too much. But what we're looking at is this is kind of the balance between these two groups of bacteria. All bacteria fall into one of these two groups. And I'll just mention, positive does not mean good and negative does not mean bad. I always have to emphasize that. It has to do with their cell wall and their cell structure. Gram-positives, why we care, is that gram-positives are incredibly resilient to drought. They're incredibly resilient to fluctuations in temperature or temperature extremes. And so if we start to see gram-positives dominate in our soil landscapes, that means that they don't really have a very good environment. Sometimes that's because it's just cold out. I'm not asking you to change the temperature outside. But sometimes it's because we didn't create or give the opportunity for that environment to be stable. Ground cover, minimum disturbance, those things all lead into it. Or even too much fertilization, we can change this community, this composition. So that's the one thing I want to mention about this one. This one I did not talk about today, but it's a fun one because when I told you that we're extracting fats, how many of you have heard of saturated fat? Unsaturated fat? There you go, you understand that. That is what we're doing. We're measuring saturated versus unsaturated fats. Now, what happens when we cook are there any vegans in the room or vegetarians? I don't want to offend anybody. Okay, what happens when we cook that beautiful 4 pounds of bacon? I said 4, not 1. We get a lot of grease, right? And what happens if you take that grease and set it out on the countertop? Let it cool down. It gets hard, right? It gets solid. Those are saturated fats. Unsaturated fats stay liquid at room temperature. Microbes change the composition of their cell membranes based on environment. Saturated fats are the most stable. They like saturated fats. However, what do you think happens when it starts to get cold? You're basically, that cell turns into a rock. They can't have that. Or when it starts to get dry. And so they change this composition because the only way a bacteria can get something in and out of the cell is across this membrane or through channel proteins on the membrane. So the lipid membrane actually is what they call a fluid mosaic model. It actually flows. Saturated fats don't flow well when it gets cold. So this is why we measure this. And what we're looking at is we want to see a ratio here that tells us a little bit about this environment. So we want this ratio to be between 2 and 3 to 1. In other words, 2 to 3 times more saturated fats than unsaturated. It's just a stability index, but it's a really quick reference for you to look at and say, why is that happening? And I know you're going to sit there and tell me, well, it's cold outside. But the funny part is what you'll see as your soils get healthier, your soil's more resilient to that environmental impact. And so we don't have these huge up and down swings with temperature, moisture. We start to get more of a steady microbial community. And that makes them pretty happy. Any questions on PLFA? You can fire anything at me you want, because I'll just pretend I know. I won't do that. Yes?
How about changing the saturated to unsaturated ratio? You mentioned on the other ones how you might change it a little.
Yeah, so what do you do from a management standpoint? Basically what you try to do is you try to mitigate allowing your soil to have those extremes. And so what I mean by that is, if you've got a hard pan 3 inches down and you get a rain, the top 3 inches are going to be completely saturated. They don't like that, and they'll change that composition. Keeping the ground completely bare, the sun's beating on it, that soil can reach 120 degrees or more. And so they'll change, keep the ground covered. The opposite happens in the wintertime. Keeping the ground covered can help keep the temperature a little warmer. So those are the types of things you can work on. Any others? Okay, if you come up with anything, holler at me. So now I'm going to get into the Haney test. And this will be a lot of newer information compared to the individual consults. PLFA is pretty easy to cover. The Haney test is a lot more in depth. There's a lot more going on. So I'm going to break it down into these components. Basically, we have soil NPK, and I don't just mean NPK, soil fertility. We've got organic nitrogen, organic phosphorus, microbial biomass, water extractable carbon, and a C to N ratio. Here's that C to N ratio again. This is a little different concept, but we're going to go through each one of these a little bit. I'm going to start with the fertility part. So when you send a soil off to a laboratory, the laboratory is going to take that soil and it's going to expose it to different chemistries. in the soil. So how many of you have heard of Malic 3, Olson, Bray 1? Those are all different extracts to basically look at phosphorus, for example. Now they use Malic 3 for other things. So this process works no differently. It's just that we're coming at it with a different perspective. Dr. Rick Haney works for the United States Department of Agriculture with the ARS down in Temple, Texas. He has a lot of experience with soil tests. He started looking at these extracts, and his basic argument was, if we're going to try to soil test to get an idea of what is happening in nature, don't you think maybe we should use an extract that mimics nature? So he designed this extract, calls it H3A, just stands for the 4 people that came up with it, Haney, Harmel, and Arnold. And what it is it's made up of organic acids that plants produce and commonly leak out of their roots as root exudates. Why in the world, have we ever thought about plants putting carbon into the soil through liquid root exudates? Right? You guys are ahead of the game. Most people think that roots are there just to take nutrients and water up and that's it. But in reality, up to 50% of all the sunshine captured by the plant and all the photosynthate that that plant can make is lost back to the soil because the plant wants it to go there. This extract is designed to try to mimic that process. That's the idea behind it. Trust me, your soil will never ever be exposed to Malic 3 extracting solution anywhere other than a laboratory. And you better be really grateful that it's not. It's not saying it doesn't work. It's got its own applications and its own tools, but it's made up of ammonium nitrate, nitric acid, various bases, and it's got a pH of around 2.5. It's incredibly salty. You don't really want to spill it on yourself. It's pretty caustic stuff. You would not grow anything in your soil if it rained Malic 3, I can tell you that much. So the idea here, we're going to mimic this solution. Now, the plants want to give up these organic acids because they're a great food source for microbes. Short-chained carbon energy packets. Liquid sunshine bottled up by a plant because that's what plants do. They feed it to the microbe. Now, why would the microbe do, or the plant do that? I mentioned earlier that bacteria have a seed-in ratio of around 3:1. They have a really high nutrient demand, and they are much more efficient at extracting nutrients out of the soil than plants ever wish they could be. The one thing a microbe can't do, most of them, is capture their own energy, just like you and I. I can lay out in the sun all day long, and I don't photosynthesize. At least I don't think so. I turn red, not green. So, plants feed microbes, microbes turn around and give the plants nutrients. It's a pretty efficient trading system. Now, when we add too much fertilizer to a system, I said too much. I'm not against fertilizer. Lay off that Coors. But when we add too much, it shuts down this process. Because plants are pretty lazy, like most organisms. They're not going to go through the process of capturing that energy and building these compounds and then giving them up for nothing. They got to get something in return. So on this extract, we want to measure what we think the plant sees because we're mimicking that extract. So we see nitrate and ammonium and phosphate. We got potassium, calcium, iron, aluminum, zinc, manganese, copper. I mean, there's a lot of things there. But we're trying to evaluate all of that fertility based on this. Now, the two different ones that you see up here are phosphorus and organic phosphorus. Phosphorus is it's a touchy subject, and I'm sure it's a really touchy subject out here with alkaline soils. We know what happens when you do put phosphorus fertilizer on. How much of that phosphorus fertilizer is available? Don't tell me none, but I know it's pretty close, right? That's what people want to say. Most of it gets tied up, especially in alkaline soils. The issue is that phosphorus, and things like phosphorus, yes, they're pH dependent, but it's also because we're trying to circumvent the whole process of how plants naturally acquire phosphorus. We're just trying to put it on and then shove it into the plant. So with the Haney test, we're going to measure not only phosphate, which is the plant available form of phosphorus, we're going to also measure all of the extractable phosphorus and subtract the phosphate, and what we have left over is what's called organic phosphorus. It's soluble, the plants can see it, it's part of the system, they just can't use it because it's not in the right form. Who transforms nutrients into the right form? Microbes. So now we just measured the phosphorus availability to microbes. I mentioned that all of those cell membranes are made up of phospholipid fatty acids, phospho being the key part of that. There's a lot of phosphorus tied up in microbes. So they do compete for it with plants. But once they're alive and they're happy with it, they'll actually transport it to plants. So we're using this extract to do that. The second part of this test is the microbial biomass portion. This is a pretty nice, revelation. Soil is a complex integrated living system. No kidding. The one thing we do know, though, is that organic carbon solubilized in water is what actually drives the whole system. I don't know exactly how my pickup truck works, but I can tell you that it's organic carbon called gasoline that makes the whole thing move. Right? So we don't have to understand everything about this complex integrated system. We know that carbon is at the center of it, and we know that it drives the system. The nice thing about carbon and most microbes is they're like you and I. They take in carbon, they take in oxygen, and they produce carbon dioxide and water. The opposite of what plants do. Plants take in carbon dioxide and water, use light energy, and make carbon forms and oxygen. So one of them is a building process, anabolic. The other one is a breakdown process, catabolic. We use that to our advantage. We can capture the amount of CO2 that a soil can produce. Your soil breathes just like you and I do. I eat chicken and probably too many desserts, and if I work hard enough, I will breathe out more CO2. Okay? So this is how we do it. Again, sticking with the theme of trying to mimic nature, right? We want to mimic the process. So the process here is that we have we take a soil that's been dried, and then we re-wet it in a laboratory and we incubate it at room temperature. We capture that carbon dioxide and we measure it. Because when your soil dries and you get a significant rainfall event, you get a flush of activity, the microbes come to life, and you get this push of carbon dioxide off your soil. This is a natural process. So we don't add anything to the soil, we don't spike it with anything, we just put water with it. That's it. And then we seal it up, see what happens. We do this over 24 hours because in that 24-hour period, 95% of the carbon dioxide that's going to come off that soil as part of that flush is going to happen in that first 24 hours. There are a lot of other methods out there that say, well, 4 days, 7 days, 15, we can do this for a year, but you're only going to generate so much CO2 off of it. I know you can't read this for most of you from where you're sitting. This is a ranking table just pertaining to carbon dioxide. Soil respiration, that's it. One number. There are 60 numbers on the Haney test. Here is one number, and here is what you can kind of learn from one number. So we have a range anywhere from 0 up to 200 parts per million or over 200 parts per million for CO2. Now the way I approach this is that I think of carbon dioxide or soil respiration like building a fire. I use a fire analogy. Anybody in here ever built a fire? Of course. When you go to build a fire, do you start with logs that are 2.5 feet in diameter and 6 feet long? No. And if you have a fire burning and it is burning very small, do you dump that kind of log on it? No. That kind of carbon input immediately, that's what you're doing is you're putting carbon in. That kind of carbon input immediately just smothers that fire. So if we're using respiration as an indicator of the microbial the microbial biomass, the higher the respiration, the bigger the fire. The bigger the fire, the higher the demand for fuel, carbon. It's really a pretty simple concept. It's harder in practice, right? Because how do we keep up with that demand? But it's important that we try. It's also a positive feedback loop, meaning the more carbon you put in, the more microbes you create, and then the demand goes up, so you put more in, and then that cycle continues to happen. It's an okay cycle. Everybody talks about wanting to sequester carbon in the soil, whether you're trying to increase soil organic matter, whether you're trying to increase just soil organic carbon, whether you just want to save the planet, whatever it might be, most people's goal is to get more carbon in the soil. Well, I've got really bad news. It takes carbon respiration to put carbon in the soil. It really does. Because when this cycle goes on, we have small parts of carbon that come off this cycle that basically get shunted down and stored. Just like it takes money to make money. I can't save every single dollar I bring into my pocket. If I did, I'd have like $5. No, I can't do that because I have to function, right? I have to live. So there's things that I have to buy. There's things that I have to do. But I hope that I have enough money coming in that I can take a small part of that and put it away. And the more I have coming in, that part grows. And I can keep putting more away. That's what you're doing. And if you get a chance, I know Keith Burns, Green Cover Seeds, must have sponsored this event. They did a wonderful thing with the certificates for the awards. If you get an opportunity, if you haven't done so, jump on YouTube and listen to Keith Burns do his carbonomics talk. It's fantastic because he relates this whole thing to economics and he talks about it in the context of the soil. I know it sounds really boring. It's actually fantastic. Keith's a much better presenter than I am, so it's good. But when we look at this, we can see all these rankings and we've got very low, very high, and everything in between. You'll notice that there is no average. Imagine that. So if I asked you, what's the average weather like? I hope that you would tell me, well, there's no such thing as average, because there isn't in this case. It's on a sliding scale because everybody's soils are different, and I don't mean just your farm to the farm next to you. I'm talking this region of Colorado versus Idaho versus the San Luis Valley in Colorado versus Nebraska. They're all different regions and they have very different climates. So there is not an average. But with a group of people like this, you can kind of establish an average. And this is what we've done in a lot of places, is you determine what that average is in your area. And then you can make adjustments to that or you can learn from that. So when we talk about the implications, if we have a really small fire, there's a very little potential for activity, microbial activity, slow nutrient cycling, residue decomposition can be 2 or 3 years or greater. We do see this all the time, especially in continuous corn operations. Really high, and I know I use corn because that's what I'm familiar with, but really high corn, or high yielding corn, continuous, you got lots of carbon, but that residue just sits there. They can't get it to go away. So what most people are doing now is they're baling it. And that started in 2012 in my part of the world when we had the drought. So people started baling corn stalks and they never looked back. Pretty detrimental though. On the other end of the spectrum, when we get in that high and very high area, we've got really fast recycling, we've got really fast residue turnover, we've got a very high potential for nitrogen release. Your nitrogen fertilizer reduction can be substantial. And I'm talking about hundreds to 200 pounds an acre, substantial. There are operations that are growing 150 bushel corn on 0 units of nitrogen. And corn's a pretty high demanding nitrogen crop. We see the same thing with 60 and 70 bushel wheat. We've seen the same thing with barley. It can happen, but it's getting the nitrogen out of this biological system and they will do it for you. So the other thing I want to mention is that you can influence this by management. It's not just carbon, by the way, using that analogy of the fire. So it's not just carbon. We can adjust things with living roots, the root exudates, they take care of a lot of this. Manure application, there are a lot of things you can do to build a fire, and it's not just the carbon part. Sometimes it is a fertility issue, and we will, and if it is, I recommend addressing it. I think I gave a few people today recommendations for addressing certain fertility issues. But it's hard to build a big fire if all you're doing is using lighter fluid. And that's what synthetic nitrogen is. It's really lighter fluid. And it allows us to burn up more carbon. So you just have to offset that. You have to have more going in. The next part of this is the soil organic nitrogen and the water extractable carbon. I skipped over the first one. We grouped these together because it's a lot easier to kind of go over them together. So the way this part works, this is pretty scientific, it's pretty complex. We use water as a soil extract. I've taken 8 years of chemistry so I could put water to soil and do an extract. The best part is I didn't even come up with it. So I asked Rick Haney one time, I said, Rick, I called him up, I said, Rick, water with soil, seems really simple, man. I don't quite understand. And he goes, well, Lance, last time I checked, it rained water. That's funny because I couldn't argue with it. And I said, yeah, Rick, I think you're right. And I asked him, I said, now in all your infinite wisdom, Dr. Haney, I said, I can't believe you had to go to school for 12 years to figure that out. And he says, well, you've been going for 10 and you still haven't figured it out. And Rick and I get along really great. It really is. That's why we're using water. It rains water. And on this water extract, what we're doing is we're trying to evaluate what the microbial habitat is. How much food do they have available? How much protein do they have available? What's the balance between the two? Now, as a producer, I'm concerned with this, or I care about this, because if they have food and if they have protein, they consume food and they mineralize nitrogen. This is what, and when you're using cover crops and when you're using manures and compost and, fish emulsions, Mike, and when we do these things, we're adding sources of organic in, but organic nitrogen is not available to the crop. The microbes have to make it available. So we can put all the organic in out there we want, but they got to release it. And so that's why we want to evaluate, but it takes energy to do that work. So we balance this out. So all of these things come together, and at the end we have what's called a soil health score. So how many of you familiar with soil organic matter? Just 3 of you, great. Fantastic. I thought that was a no-brainer. Okay. How many of you are awake? Okay, a few of you. Elizabeth, hey, I'm awake. I'm eating this up. Okay, good. Soil organic, I'm barely awake, by the way. Soil organic matter. We focus on soil organic matter so much. We talk about it. It's been around. They've been testing it for 100 plus years. Soil organic matter is basically the quantity of organic carbon in your soil. It is the house the microbes live in. The bigger the house, the more microbes you can hold. Also, the more water you can hold and all of those things. The problem is that it's the house. We want to know how much food is in the house. So on the Haney test, we measure what's called water extractable organic carbon. What fraction of carbon, this is a small fraction of the organic matter, but what fraction of it is soluble food? Anybody have kids? Okay, that's good. I asked that question in front of a room of 500 people in Kansas a couple weeks ago, and nobody raised their hand, and I just said, thank you. They didn't think that was funny. So you got kids. Now, anybody got teenagers? Few, okay. Had teenagers? Okay, now what happens if you don't have any food in the house? What do you think I did as a teenager? Look at me. What do you think I did as a teenager when there was no food in the house? Bingo! Eat the furniture. I'm going to start telling everybody that. Eat the furniture. They burn the house down. They tear things up. Because I'm hungry, darn it. I know I ate an hour ago, and I know it was a lot, but I'm hungry. Microbes are hungry. And if you don't put food in the house, they start to consume the house. In other words, as Ray Archuleta would say, you lit the house on fire to barbecue a hot dog. But they do, and if you think about it, it makes sense. If you are programmed to survive at all costs, because most organisms on this planet don't have the luxuries we do, it is survival of the fittest every day, all day. That is your one job, is to literally survive and make more of yourself. So if you're an organism in the soil and you can't find any food, but you've got a whole bunch of carbon tied up in the house, you start to eat the house. We've done a really good job of this in agriculture for 150 years. Our input of carbon is generally not high enough to keep up with that demand, especially in row crop systems. In my part of the country, 7 months a fallow. How many of you have livestock? How many of you feed livestock for 5 months out of the year and then check on them in 7 months? That's essentially what happens when we go after a corn crop or a bean crop. So I'm not here to say we shouldn't grow row crops. We should. We have to. But this is what is happening. It just, I don't have all the answers how to fix it. I'm just saying this is what's going on. They starve. Unfortunately, we had a really kind of sad scenario not too far from my house. We had somebody with cattle in a pasture. They are now in jail because they left those cattle in that pasture and basically got thrown in jail for animal cruelty. Now, I can't change that, but the one thing I can say is that after driving by, you will be amazed what cows will eat if you build a fence high enough and strong enough. They were stripping bark off trees, they were chewing on fence posts. I mean, they dug the whole thing up. There was nothing left to survive. So, I'm sorry to beat this into the ground, but this is really important because we focus all of it on soil organic matter. I don't care about soil organic matter other than I just want to know what it is. After that, I just want to see it go up. But it takes food to make that happen. We got to build a bigger house. The other thing we measure on the water extract is the water extractable organic nitrogen. So I said we did organic carbon, now we'll look at organic nitrogen. This is all that nitrogen that is not in nitrate and ammonium form. Most soil tests focus strictly on nitrate. If you're lucky, you get ammonium. And if you go east of the Mississippi, I know that's a long ways from here, guess what? They don't even measure nitrate. They don't measure nitrogen at all. They just assume that whatever you put on the year before is gone the next year. No reason to test for it. Matter of fact, at the University of Florida, we had some soil samples come in. We went to run nitrogen on them, and they said, no, don't bother. Sandy soil, sandy loam soil. We get, look at all the rain we get down here. There's no nitrogen left. Well, we'd already run them. Over 200 parts per million nitrate. 400 plus pounds of residual nitrogen in that soil. The University of Florida said, that's all right, put on 260 units. Because they just have it ingrained in their mind that there is no nitrogen left in that soil system. So the problem is that's an extreme issue east of the Mississippi. I poke on everybody east of the Mississippi, but then you come out to the Midwest and we're sampling, or we test for nitrate. And like I said, if you're lucky, you get ammonium. Well, what happens when you got a system that you're trying to get away from operating on nitrate? I mean, you're focusing on growing cover crops to tie up residual nitrogen. You're talking about putting in legume cover crops, brassica cover crops. You're talking about integrating animals. If we just measure nitrate, we're missing a huge part of the picture. Because in those systems, nitrogen does not just exist as free nitrate. In native systems, if you go to measure nitrate or nitrogen in those systems, it's generally very low. And I mean less than 1 to 2 parts per million. Because as soon as it becomes available, the biology ties it right back up. It does not like free nitrate. There's a reason why free nitrate in our drinking water over 10 parts per million is toxic. We don't like it either. So again, not against it. I'm just talking about the differences in the system. We got to have it. In a lot of cases, we got to put on some fertility, but the further down this road you go, the less useful nitrate tests are, and these are the more useful ones. So I talked about these different sources. Now, the reason why organic now a lot of people say, well, it's still soluble, it's still water soluble, so aren't we going to leach it? Now, maybe not in this part of the world, but are we going to leach it? Are we going to volatilize it? Is it going to run off? It can, but the risk of that happening is so much lower compared to nitrate and ammonium because microbes are losing carbon when that happens, and they don't like to lose carbon. So they tie this stuff up pretty quickly. Most of the organic in the system is actually tied up in those bacteria that are 3-to-1 nitrogen, carbon to nitrogen. And they're little bags of fertilizer. And so the key to getting it back then is to have the other microbes eat those microbes. And when we look at this, we talk about the carbon and nitrogen balance. This is the key to get it back. So organic carbon and nitrogen have to be balanced to get that highest return from that bank account. When that carbon and nitrogen ratio is above 20-to-1, keep in mind, this is the 20-to-1 is coming from the water extract on this test. It's not the seed-in ratio of your cover crop. It's not the seed-in ratio of your cash crop. It's just off this test. When it's above 20-to-1, we don't give you a nitrogen release credit. Microbes' affinity or demand for nitrogen is too great. They're not going to give it up. They got plenty of carbon. I don't need carbon from the plant. I'm not going to give you the nitrogen for your carbon. I'm going to hold on to it. It's mine. Microbes are like little mafia people in the soil, okay? They can get their cut. Now, we want to get this ratio somewhere between 8-to-1, 8 times carbon and 1 part nitrogen, or 15-to-1. Ideally, we really want it between 10 and 12. That's the right balance between energy and protein. Now, going back to my kid analogy, since a lot of you have kids or have thought about it maybe. My wife does a lot of traveling, and I've got a 3.5-year-old daughter and an 18-month-old son. And the first time my wife left the house, she was kind of nervous, and I was completely terrified. But she gets on a plane, goes to Mexico, and of course she calls. Matter of fact, she just flew into Denver here about 20 minutes ago and was on her way home. And she called me up and she said, "Hey, did you feed the kids this morning?" I'm like, "Duh." I got it handled. I'm not a monster. Of course I fed them. She goes, "Oh, what'd they have?" I said, "Ashlyn had Coca-Cola and Pixie Sticks." I could hear the wheels lift up on the plane as she was coming back to kick me, right where it counts. And I'm like, well, what's the problem with that? She seemed pretty happy. Ran around the house, punched some holes in the drywall. She was great. 2.5 years old. It's all carbon, right? You don't have to be a doctor to understand that if you go to the doctor and tell him that that's what you're eating for breakfast, he's going to say what? That's a lot of empty calories. It's just sugar. It's just carbon. It's nothing there. So I went ahead and I thought, okay, I'm pretty smart. I'm going to fix that. So for dinner, we had Flintstone vitamins. Took care of it. That doesn't work either. Now, I didn't honestly feed my kids Coca-Cola and Pixie Sticks and Flintstone vitamins. She got them herself. She knows where they're at. So the point is that you have to balance energy and nutrition. Some of us can do a little better job of balancing energy. I get a little too much, but it's still a balance. And that's what we're doing here. And when we balance this, if we get a ratio below 8:1, we might have all the organic in we want. We can't get the microbes to release it because they don't have any energy. Can't do it. And on the other end, when it's high, they're going to tie it up. They got all the energy in the world, but nitrogen's a hot commodity to them, so they hold on to it. So, anybody here from the university system? Oh no. Okay, I got one, I'm just kidding. I'm a product of the university system. Kinda, I didn't really go there per se, but they tried to claim me. So, the university, and I'm just going to use corn because I'm just making an example because I don't know all the nitrogen requirements of all the thousands of vegetable species everyone's growing in this room. I could do wheat too, but corn, if you go to the University of Nebraska at Lincoln and you ask them, how much nitrogen does it take to produce a bushel of corn? They recommend 1.1 pounds of nitrogen per bushel. If you go to Iowa State, it's somewhere, I think, closer to like 1.3. Kansas State's 1.4. There's various numbers, and I don't know if those are the exact numbers. My point is, I think Nebraska is 1.1. My point is you ask all these different universities how much nitrogen it takes to grow a bushel of corn, and they give you these types of numbers. And the wheat's even worse. I talked to somebody at the University of Montana, and they told me 3.6 pounds of nitrogen per bushel of wheat. But in Nebraska, we're at 2.4, and I think K-State's 2.6. But here's the funny part. Does anybody know how much nitrogen is in a bushel of corn grain? 0.67 pounds. I don't care what hybrid you're growing, and I don't care what state you're in. It's on average 0.67 pounds. So the university tells you, put on 1.2 pounds and you're going to capture and remove, if you're not baling all those corn stalks, you're going to capture and remove 0.67 pounds. Where'd the rest of it go? Remember that mafia I told you about? If we don't feed them, they tie up nutrients because that's the only play they've got. That's their bartering chip. They're going to hold on to those nutrients. They're going to tie them up. And they're going to use those nutrients, especially nitrogen, to burn the house down. So that's why we've overcompensated for a leaky system. Again, it's not the nitrogen fertilizer that's really the issue. It's the fact that we've shut the biology down, and then that leads to putting more of that on. One last thing I got to ask when it comes to nitrogen. Oh, hey, there's that beer. Speaking of carbon, I like my liquid bread. Very little protein in this, by the way. How much water does a 5-gallon bucket hold? Anybody want to volunteer? Winner, 5 gallons. Not a trick question. 5 gallons. Okay, now what happens if I poke a bunch of holes in that bucket? How much water does that 5-gallon bucket hold? 5 gallons. The volume of the bucket did not change. The problem is that how much water do I have to pour in the top continuously to keep 5 gallons in that bucket? When you have a very leaky system, and I mean inefficient system, inefficient meaning nutrient transport, nutrient uptake, the way we've learned to overcompensate for that is the classic human response. Well, just put on more. Because we can make up for that inefficiency by just doing more. I do the same thing. I'm a really terrible fisherman, but I love to fish. You know how I increase my odds? More rods. 6 poles instead of 1, and guess what? You increase your odds. I don't try to get better. I don't try to learn. I just throw out more lines, right? And so that's the point. It's thinking about the system that way and understanding that we can actually, through management, patch those holes and start to fix that system. There are a lot of producers now that are producing corn between 0.5 and 0.75 pounds of nitrogen per bushel. Can live with that because that's a very efficient system. If you're removing 0.67 pounds in a bushel, you should be able to produce corn on that, or at least close to it, right? So here's some of the stuff with the seed-in ratio. So here's the implications for it. We've got a ratio result of greater than 20 to 1 down to 8 to 1. Here's your ranking: poor, marginal, good, ideal, and poor again, because this is a bracketed one. So we talked about the nitrogen implications. You know, we talked about the tie-up or the release, but here's the management side of it, and this is just a small list of things. If you got a too high of a seed-in ratio, makes common sense. We're going to increase legumes in the rotation or in the covers. We might reduce high carbon inputs. We might graze longer to remove more of that carbon. And again, these are just 3 or 4 ideas. There are countless ideas, and it depends on your operation, what you want to try. But focus on reducing the carbon. Oh, you want to reduce it a little bit, or you want to bring in a shot of organic in. Manure, compost that have high organic in. You know, I heard somebody mention earlier wood chips. Somebody was doing wood chips. So, okay. Oh, okay, wood chips. Wood chips, really high carbon. They do awesome at establishing a carbon system. And there are a lot of people that use them and bring them in. At some point, that really high carbon residue, eventually you'll end up with a situation where you've got a really high seed-in ratio. But it's a wonderful way to get carbon, especially when you've got subsoil and things there. You want to get organic matter into that. You want to get carbon into it, and you want it to last a while. And wood will last quite a while, typically, relative to like soybean residue or things like that. So, but this is kind of how we do this, and through management, you can adjust that ratio by the different things you want to put in, the different crops you grow, and how you manage those crops. So this is just tied to the ratio here. Yes?
Do people do Haney tests on like compost that they make, and does that make sense in terms of what you're applying to the fields?
Yeah, we have run compost for Haney tests quite a bit. We look at the respiration, you know, we run the same test. As far as, because of the calculations of the Haney test work as if it's a soil. And what I mean by that is there's some assumptions being made. When we take a soil, we're thinking, okay, there are 2 million pounds of soil in 1 acre to a depth of 6 2/3 inches. So you'll hear a lot of people say you take parts per million times 2 and you get pounds per acre. That's kind of the conversion. When we start talking about compost, typically, we're not talking about 2 million pounds, and we're not going to apply 2 million pounds unless you want to put compost across an entire acre 6 2/3 inches deep. If anybody makes compost, talk to the guy who wants to buy that much compost. So the way we do that is we just have to make some adjustments to the calculations, because typically when we report nutrients on compost, we do it a little more like manure. It's like % nitrogen per ton or per pound, and we have to know the moisture. So we can actually truly evaluate just how much phosphorus is in that compost or how much nitrogen's in it. But it can be done. We have done it. It works really well for the seed-in ratio part of the water extract, and it works really well for the microbial respiration part. So it's a good question. And we've run several hundred of them that way. So finally, on this Haney test, we bring all this stuff together and we get what we call the soil health calculation, soil health score. Basically, the way Rick describes this is it's the overall health of your soil system. Now, I wish that it wasn't necessarily called the soil health score, because there are a lot of other things that go into soil health that aren't measured on this test. So this is a really good tool, but it's not all encompassing, right? So there are other things. But it combines several independent measurements of your soil's biological and chemical system. It can range anywhere from 1 to over 50 on this score. I mentioned to most of you today that I talked to that we like to see the score above 7. So we start at 7. We want to see it above 7. I asked Rick, quite a while ago, I said, why 7? And his answer was, why not? So, no, I'm just kidding. He did say why not, but then he explained to me what he was talking about. So after looking at thousands and thousands and thousands of these, basically when you get to that score of 7, that's when we start to see positive things happening in the soil. That's when you start to see a release of nitrogen that means something to your pocketbook. It's where you can start to reduce some of your fertility without an ill effect. I said reduce, you don't go out and just eliminate. But that's where that number tends to start. We use this to help track effects of your management practices, obviously, and then we use it to help calculate a cover crop input. Now, the cover crop input, it's not even a recommendation. It's what we call a suggestion. What's the difference? I don't know. People like to think recommendations are kind of like held in, like biblical. This is set in stone. This is what the lab's telling you to do. We're not telling you to do anything. This is just a suggestion, and it's grasses versus legumes. Mostly, and we're just doing it based on the soil health score because we're evaluating what that demand is for carbon. We don't want to plant a cover crop that's 90% legumes if you know that you don't have enough carbon out there, or vice versa. So there is a suggestion, it's based on the score. Here's how that score is calculated, and it's just the red bar across the top. It's pretty complicated. Soil respiration divided by 10. Water extractable organic carbon divided by 50, and water extractable organic nitrogen divided by 10. I can even do that math. Maybe not in my head at this point today, but I can still do that math. It's not incredibly complex, but it's self-balancing to the point that when your carbon goes, or when your CO2 respiration goes up, typically it's because your carbon went up, but if your CO2 respiration stays up for very long, your carbon goes down. CO2 goes up, score goes up. Carbon goes down, score goes down. And the reason why it's designed that way is because we know it's variable. We don't want you to run a test and score a 5 and then come back and run a test and score a 35. Just because one thing changed a lot. Because how do you track that, right? And then the next time you do it, it's a 7, and then, so he tried to make this so it's self-balancing, so when you're actually seeing changes, it's true changes. And you're looking for a trend line over time, is what you're really after. Inorganic nitrogen is just nitrate plus ammonium. Organic nitrogen is total nitrogen in the water extract minus the nitrate and ammonium. I mentioned earlier organic phosphorus is total P minus inorganic P with the H3A extract. The one I want to talk about a little bit is microbially active carbon. I mentioned this to a few people today. The microbially active carbon is how much of the water-soluble carbon in your soil was acted upon by the microbes. If you have 200 parts per million and your respiration was 100, that's simple math, 50%. 50% of the carbon was affected or acted upon by the microbes. Now, the reason why that's important is because I mentioned burning the house down. This is an indicator of how much food versus what your demand is. So if the percent MAC, or microbially active carbon, is less than 30%, what you have is you've got a lot of food, your respiration demand is pretty low. So there's something else in that soil system that's kind of limiting that respiration. It's not a lack of food. If it's above 80 and it stays above 80, don't ever panic if you get one that's above 80. It's just if it stays there for a long time, the demand for carbon is greater than what the supply is. Well, I can tell you right now, if me and my buddies get together, we don't buy one pizza because the demand is greater than that supply, right? We also don't buy one beer. But we don't want that to happen because then the microbes start to burn the house down. And so that's what we're trying to evaluate here. A lot of people ask me, where should some of these numbers be? The water extractable organic carbon, most soils I've analyzed range between 50 and 800. I think I saw some ranges today looking at results somewhere between 150 all the way up to 600 on a few soils. Most of them did fall pretty close to this, between 100 and 300 range. Okay, to give you an idea of where you're at. Now the water extractable organic nitrogen, we kind of see the same thing, between 5 and 10, most between 10 and 30. Keep in mind though, this is in parts per million, so that's 20 to 60 pounds. So at 100 part per million, that's 200 pounds. It's a lot of nitrogen. Organic phosphorus, between 2 and 50. Typically the higher your inorganic phosphorus, the higher the organic. And we saw that today on a few tests where we've had long-term manure application. Or compost, some of the phosphorus tests, the organic fraction was 30, 40, 50 parts per million. The inorganic was 150, 170, 200. But that's typically how phosphorus behaves. And we get the microbes to basically convert that over to make it available. Real world example. So the first step, look at the soil health score. Then we want to focus on those individual components that make up that score. And if everything looks great, except we're trying to figure something out, we want to look at the pH, soluble salts or EC, electrical conductivity, and then some of the other nutrients for limitations. We can have limitations. We had a couple soils where phosphorus was less than 2 part per million. That's a limitation, not just for plant growth, but for microbes. Recognize the primary concern or concerns, and then design a management plan, and then we want to test again. So here's 4 samples. I did not pull everything out. It's a lot of the stuff we talked about today for the people that did some consults. Yes, it so happens that they're in order ranked by soil health score, ranging from 6 to 13. You'll notice that as the soil health score goes up, respiration goes up. The interesting part is the water extractable organic carbon is actually the highest on the worst soil health score. So if I do quick math and I say 190, or actually go the other way around, 13.8 divided by 190, I get like 6%. So 6% of that carbon is being used by the microbes. Do I have a lack of food? No. My microbial demand is pretty low. I don't have a lack of food. I got plenty of carbon for those microbes. Matter of fact, my carbon to nitrogen ratio is 19.8. I got a lot of carbon. You'll notice the implication of that low soil score. My organic nitrogen release is 2.8 parts per million, which is 5 pounds or 6 pounds to the acre. Not even hardly worth messing with, because most applications you can't even get down to that kind of level. The reserve is closer to 15 pounds. pH is 7.9. As we go through these, make some of these comparisons. I'm not going to go through every one of these, but notice on 3 and 4, the organic nitrogen release is maximized. We're getting all the credit. The problem with number 3 is that the carbon to nitrogen ratio is 5.1. 5.1. That came off a field that's been 31 years continuous soybeans. Nobody thinks that's terrible? Nobody? Nobody? 31 years continuous soybeans, for crying out loud? What do you think that carbon system's like? That darn soil looked a little bit like this floor, but I'm guessing this floor has got more pores in it. I mean, there's nothing there. Now, it respires. It generates. Where do you think that carbon's coming from? The house. That's your head. They're taking it out of the house. And they're mineralizing nitrogen and doing all this stuff. And soybeans don't care. They don't want the nitrogen. They could care less. So the big concern on number 3, and to some extent number 2, is carbon. Lack of carbon. When we get to number 4, we end up with this. So here's basically the summary. The first sample, phosphorus is incredibly low. That limits respiration along with pH being high. Number 2, carbon and P are both limiting still. Number 3 is just easy. It's just carbon. Carbon is the big problem. You got to get out of soybeans on soybeans on soybeans. Say that 31 times in a row. Sample 4, overall pretty good. We got a pretty good carbon and nitrogen balance at 15. The goal is to keep up with this intensity to drive up that microbial activity. So in other words, don't do anything drastic. Just keep doing what you're doing, but you just need a little more time. Remember, it took 100 years to degrade soil down to where we started from. Most of us. You get to the southeast, maybe 200 years. It's going to take a little bit of time to build it back up. But these are a couple real-world examples. And I want to talk about the fertility recommendations. I got like 2 slides on this, and then I'm about done. A lot of people tell me, if you talk to anybody about the Haney test, a lot of people say, well, you can't do fertility recommendations off the Haney test because the Haney test isn't calibrated, and it doesn't make any sense. And I say, well, I'm going to tell you that conventional soil tests aren't calibrated. And they look at me and they say, how can you say that? And I said, calibrated to what? What are you calibrating it to? Conventional soil tests were calibrated to fertilizer response curves. So back in the 50s, they took a whole bunch of soil that we had basically mined most of the nutrients out of because we didn't have fertilizer before then. Some nitrogen, but not a whole lot. It wasn't widely used. They would grow a crop and then they would dump some fertility on and they would go, wow, look at that response. Let's plot that on a curve. And then this is how we're going to tell you, based on the soil test level, how much of this nutrient you should put on. It increased production a lot, and it worked okay. The issue is that, here's my argument, conventional soil tests are calibrated for conventional farming. How many of you, by show of hands, would call yourself conventional? By whatever definition you want to use. I'll show you conventional. Come to Kearney sometime. Kearney, Nebraska. I'll show you. You can drive around. We would struggle to find somebody who's doing anything other than what their neighbor's doing. The only problem is that when people do that, everybody ends up doing the exact same thing because you do exactly what your neighbor's doing. The Haney test, while it may not be calibrated, the argument is that if you're not farming conventionally, those conventional soil tests are not calibrated for your system either. They don't measure the things that you are providing through your management. Conventional tests do not see organic N. They do not give credit for it. They don't care about microbes. It's pH, NPK, done. So, the further down the road we get into regenerative agriculture, the further away from conventional soil tests we need to get. I tell people all the time, match the right tool to the right situation, right? So here's how we make recs. The conventional way, you tell us what crop you want to grow, tell us what yield goal you've got, We figure out the total amount of nutrient required, and when I say we figure it out, I don't mean we. IPNI, the International Plant Nutrition Institute, they have that information. How much nutrient is in a plant for various nutrients. We take that information and then we start measuring, that's your total amount needed, and then we measure things. So for nitrogen, we give you credits from soil tests. On the conventional side, it's nitrate only. Then you get a credit for past crop potentially. You get a credit from subsoil. Some people take credits from soil organic matter. Some universities, some laboratories say, well, for every 1% soil organic matter you have, you can get a 25-pound credit for nitrogen. I have bad news. If you take nitrogen out of the organic matter, what do you have left? It's not organic matter. Trust me, I would eat cake all day if I could still have cake after I eat cake. Right? You don't. You don't have organic matter anymore. You can't take nutrients out of it and still have organic matter. And then you get credit from irrigation water. This is really big in Nebraska. We have nitrate problems in certain watersheds, and we encourage people to run irrigation water to figure out if they have nitrogen. We want them to take that credit. On the Haney side, I don't have to read it, but I'm going to skip the first three because it's exactly the same. The credit from the soil test includes nitrate, it includes ammonium, it includes organic nitrogen release. Guess what? The last three are still the same. With the exception is we definitely do not give a credit for organic matter on the Haney test. Not directly. We don't measure organic matter and just say this is what your credit is. We're doing that through the organic nitrogen release, the water extract. That's how we're doing that. But they're really pretty similar. The concept's exactly the same. So here's an example, and again, here's corn. I know, I'm sorry. I could do onions, but I don't know what it is. Here's the numbers. Oh, conventional corn, if we say 200 bushel yield goal, 1.1 pounds of nitrogen per bushel, 220 pounds requirement. Pretty simple math. Throwing some numbers in there, here's 10 part per million nitrate, 20 pounds. Soybeans, we give a past crop credit of 40. If we don't run subsoil, we assume it to be 25 pounds. I am not the person who came up with that. That was Dr. Ray Ward. He's one of the most brilliant soil scientists I've ever met, and if he says that's what it is, I trust him on it. 25 pounds. Go to the Haney side, you've got the same requirement, same nitrate. Now you got ammonium and organic nitrogen release. The soybeans is the same and the same subsoil credit. Nothing's changed. Except at the end of the day, your total requirement or recommendation coming out of the lab on a conventional side is 135 units. And on the Haney side, it's 95 units. It doesn't take a lot of $50 soil tests. Yes, that is what this costs. It covers 40 acres. It's $1.25 an acre. It doesn't take a whole lot of nitrogen savings to make up $1.25 an acre. 40 pounds of nitrogen across 40 acres is quite a bit of money. But it truly is a credit that we've just been ignoring and putting on. As your soil health increases, this number gets bigger. But I will mention, the nitrogen credit from the organic side will never be higher than what we measure on the test. In other words, if your organic nitrogen is 20 pounds in the water extract, your credit is capped at 20 pounds. Max. I don't care how high your respiration is. I don't care how good your seed-in ratio is. And the reason we do that is because we're not trying to overpromise and underdeliver. That's a really bad thing to do. I don't run very fast, and I don't like pitchforks. I don't want to tell people to cut their nitrogen by 150 pounds just because we think it sounds good. We're trying to do it based on what we measure. And this is what we measure. Using conventional tests, and I mentioned this already, but using conventional tests and fertility requirements can lead to excess fertilizer being applied in regenerative ag systems. How many of you know Gabe Brown? You know the name Gabe Brown in North Dakota? Okay, I like to pick on Gabe. Gabe and I are pretty good friends. We have a lot of things in common. So anyway, we ran some soil tests. I remember, this is before I'd ever met Gabe. I ran some soil tests for him. And I said, Gabe, we ran these, and his nitrate and ammonium came back at less than a part per million each. The organic N was almost 90 or 80 parts per million, or 160 pounds to the acre. That's the organic nitrogen pool. That's just how big it was. He had corn in Burleigh County, North Dakota, and a yield goal of 140 bushel. According to the Haney test, his nitrogen recommendation was 0. Put on no nitrogen. I'd never seen this, so I had to call this guy who I'd never met, and I had to say, Gabe, my name's Lance, it doesn't matter. Listen, I got to talk to you about your soil test results. And I said, this is what they tell me, and I don't really know how to say this to you because I was afraid he was going to crawl through the phone. And he said, yeah, that sounds good. I wasn't planning on putting any on anyway. Okay, let me know how that works. He did. He grew 136 bushel corn. Dry land. I should also mention this was 2012. You guys remember 2012? The county average in Burleigh County was like 64 bushel, maybe. So, point is, we all know the one thing all universities and agronomists can agree on is that most crops require nitrogen. And we think legumes don't require nitrogen, but in fact they require even more nitrogen. We just don't have to give it to them. But he produced corn with 0 nitrogen. And according to the conventional soil test, he needed to put on 150 units in, minimum. That's a lot of money. And yeah, you could argue, well, yeah, but he might have yielded a little better if he had put it on. Maybe. He really might have. But is growing 160 bushel corn that much better than 135 when the county average is 76 and you didn't? I mean, it cost him $1.35 a bushel to produce it. And because he didn't put anything on, he was able to sell it at a premium for around $7 a bushel that year. I think corn was pretty high that year anyway. So, doing this, healthier soils require fewer fertility inputs due to the increased ability of plants to acquire those nutrients. Collectively, this is called the soil health effect. And it's just something I call it. I don't know, you're probably not going to find this anywhere else. But after looking at 50,000 plus Haney tests, after looking at yield data, after looking and talking to producers such as yourself, everywhere in the country, and I've run soil tests or soil samples from probably 16 different countries, this is what we hear over and over and over again. Well, according to my conventional soil test, I should have phosphorus deficiency. I should have sulfur deficiency. I shouldn't be able to produce this crop on this much fertility based on the soil health or the conventional test. I'm being told to put it on. But yet they don't show deficiencies. Not always, they do sometimes, but we see this as the soil health gets to a point, we don't see deficiencies. What we used to classify as a low phosphorus test is no longer low anymore. And so it's important to keep that in mind because I know phosphorus is a hard thing out here. So this is that soil health effect, and it really can be a big difference.